It was September 2020. The phone rang in a quiet flat in London. The world was quiet. The streets were empty. The pandemic had forced everyone inside. The noise of the city had faded down to a hum. Martin Harrer sat in his home. He shared this space with his wife. Her name is Shui Mei Li. She is a mathematician too. They were used to working from home. They were used to the silence. But this call broke the silence. The voice on the other end was from California. It brought news that was hard to process. Martin listened. The voice told him he had won a prize. It was the Breakthrough Prize in Mathematics. Most people know about the Nobel Prize. The Nobel Prize is famous. It is old. It comes with a gold medal and about $1 million. But there is no Nobel Prize for mathematics. Alfred Nobel did not create one. For a long time, the biggest prize in math was the Fields Medal. Martin already had that one. He had won it 6 years earlier. The Breakthrough Prize is different. It was founded by billionaires from Silicon Valley, including the likes of Mark Zuckerberg and Sergey Brin from Google. They wanted to create something loud. They wanted to make scientists as famous as rock stars. They wanted to give them money that could change a life. The prize comes with $3 million. Martin put the phone down. He was shocked. He had not applied for this. You cannot apply for it. A secret committee chooses you. They look at your work. They look at the impact. They decide if you have changed the course of human knowledge. $3 million. It is a number that is hard to imagine for a pure mathematician. Mathematicians do not run expensive labs. They do not need particle accelerators. They do not need giant telescopes. They need a laptop. They need a pen. They need coffee. Martin turned to Shui Mei. They celebrated quietly. They could not go out to a restaurant. Everything was closed. They stayed in. The news spread quickly online. It said that a British-Austrian mathematician had won the biggest prize in science. They said he had tamed a nightmarish equation. They said he had seen order in chaos. But to understand why he won, we have to look back. We have to look at a manuscript that appeared 7 years before that phone call. Martin Harrer was born on the 14th of November, 1975, in Geneva, Switzerland. It was a city of clockwork precision, a fitting backdrop for a mind that would one day dismantle the mechanics of time and space. He was born into the trade. His father, Ernst Harrer, was a distinguished mathematician at the University of Geneva, known for his work on differential equations. For the young Martin, mathematics was domestic. It was the language spoken at the dinner table. Yet, his intellect was not merely a carbon copy of his father's. From a young age, he displayed a voracious, almost aggressive curiosity. By age 6, he was reading chapter books. He moved effortlessly between French, German, and English. For his 12th birthday, his father gave him a programmable pocket calculator. In an era before ubiquitous smartphones, this device was a portal. It was a machine that obeyed instructions perfectly. Harrer pushed it to its breaking point. He began to understand the concept of an algorithm, a step-by-step procedure for solving a problem. His early exposure to the strict logic of programming set him apart from his peers in pure mathematics. Unlike many theorists who dealt only with abstract concepts, Harrer's thinking was rooted in processes, loops, and architectures. In high school, at the Collège Claparède, this fusion of math and code led to his first major failure and his first great success. He entered a science competition with the goal of creating software that could read a digital recording of a melody and automatically generate sheet music. He quickly realized the task was impossible. The physics of sound, which includes separating overlapping notes, timbres, and rhythms, was too complex for a teenager in the early 1990s. I realized later that such an endeavor was actually beyond my abilities at that time, he recalled. But to test his ideas, he needed a tool to view and edit the sound waves. Since he couldn't find one he liked, he wrote his own. The software he built did not disappear when the science fair ended. He named it Amadeus, a nod to the Austrian composer Mozart. Amadeus was a sound editor for the Apple Macintosh. It was lightweight, fast, and stable. It allowed users to visualize sound waves, remove the hiss from old vinyl recordings, and convert file formats. Remarkably, Harrer continued to develop and sell this software throughout his university years. While studying for his PhD in physics at the University of Geneva under the chaotician Jean-Pierre Ekman, Harrer was simultaneously running a commercial software company, HarrerSoft. The software became a standard tool for music professionals and archivists, eventually being dubbed the Swiss Army knife of sound editing. This dual life gave Harrer a unique advantage. Financially, the income from Amadeus gave him independence. He did not need to chase safe, incremental grants. He could afford to take risks. After his PhD, Harrer moved to the University of Warwick in the UK. It was here that he turned his attention to the field that would define his career, called Stochastic Partial Differential Equations, or SPDEs. Stochastic partial differential equations are a mathematical tool for understanding systems driven by randomness. To grasp the idea, consider the simple act of stirring milk into a cup of tea. Initially, the milk forms a distinct cloud, but stirring causes it to stretch, swirl into fine filaments, and fold over itself until the liquid achieves a uniform color. Classical physics attempts the impossible, predicting the exact path of every milk particle. In reality, tiny, unpredictable forces like heat fluctuations and microscopic collisions introduce noise into the system. To account for this inherent unpredictability, mathematicians incorporate a stochastic term, a mathematical representation of this randomness, into their equations. Instead of seeking a particle's precise location, they pivot to asking, what is the probability that the particle is found here? This approach proves effective for simple systems. However, Martin Harrer focused on complex systems where randomness operates continually, affecting change across both time and space. One of the hardest problems in this field is the Kardar-Parisi-Zhang, or KPZ equation, which models how interfaces grow. Imagine a game of Tetris where the blocks fall randomly and uncontrollably. Crucially, these blocks are sticky. They adhere immediately wherever they land and do not slide to fill gaps. As they accumulate, they create a highly irregular jagged skyline, which is the interface the KPZ equation attempts to describe. The equation suggests this growth is governed by three factors: the pull of gravity, the tendency for the interface to spread sideways, and the continuous random arrival of new blocks, or the noise. Attempts to solve the KPZ equation led to a major mathematical roadblock, rooted in the nature of the noise. In these models, the noise is defined as white noise, a highly irregular and completely random function that never smooths out. No matter how much you zoom in, the KPZ equation requires mathematicians to calculate the slope of the interface and then square that value. Because the interface is so jagged, its slope is effectively infinite. Squaring infinity yields a larger infinity, resulting in the impossible operation of subtracting infinity from infinity. Mathematically, this is undefined, or nonsense. The KPZ equation was considered ill-posed for many decades. Although physicists were certain it accurately modeled natural phenomena, including the growth of bacterial colonies and the patterns found in burning paper, mathematicians had not been able to formally prove that a solution to the equation existed. In 2014, Harrer introduced regularity structures. He realized that standard calculus, which uses smooth shapes, polynomials, to approximate curves, was the wrong tool. It was like trying to build a cloud out of square Lego bricks. Harrer created a new set of building blocks. These were rough, jagged, probabilistic objects that mimicked the noise itself. He built a new algebra to handle them. He also used a technique called renormalization, borrowed from particle physics. He compared it to a microscope. If you look at the noise with a blurry microscope, the equation makes sense. As you sharpen the focus, the numbers blow up. Harrer showed that by subtracting specific counterterms, essentially calibrating the equation as you focus, you could get a stable, finite answer. He turned infinity minus infinity into a precise number. The impact was immediate. In 2014, at the International Congress of Mathematicians in Seoul, Harrer was awarded the Fields Medal. It is often called the Nobel Prize of Mathematics, but it is awarded only every 4 years to mathematicians under 40. Harrer, then 38, accepted the award with characteristic calm. He had gone from a modest academic to a mathematical celebrity, but his demeanor didn't change. He was still the guy who liked Pink Floyd and coding. 6 years later, in September 2020, the world was in lockdown. Harrer received a Skype call at his London flat. It was a notification that he had won the Breakthrough Prize in Mathematics. "It was completely unexpected," Harrer said. "We couldn't go out or anything, so we celebrated at home." When asked what he would do with the money, his answer was practical. "London is expensive. We are still renting," he noted, "so it might be time to buy a place to live." Behind the solitary genius narrative often lies a partnership. For Harrer, that partner is Li Shuimei. Li is a brilliant mathematician in her own right, specializing in stochastic analysis. They are not just husband and wife, they are colleagues. They have co-authored papers, tackling complex problems like averaging dynamics driven by fractional Brownian motion. Their life is a shared orbit of intellect and domesticity. They have navigated the two-body problem, the challenge of finding 2 academic jobs in the same city, moving together from Warwick to Imperial College London, and later to EPFL in Switzerland. Li describes Martin with affection. "Martin likes to talk to people. People like to talk to him," she said. "They find respite in cooking. They experiment with fusing Chinese spices with Western ingredients." And yes, Martin still maintains Amadeus. Even as a knight of the British Empire, as he was knighted in 2016, he answers customer support emails from users wondering why their MP3 files won't open. Even today, he is listed as the primary customer support agent on Harrersoft website. Harrer is a citizen of the scientific community. As an Austrian living in the UK, Harrer was deeply concerned by Brexit. In 2018, he joined 28 Nobel laureates and other fields medalists in signing a letter to political leaders, warning that science requires the free flow of people and ideas. He argued that erecting borders would stifle the collaboration that drives discovery. In a 2025 interview, Harrer argued that while AI is good at synthesizing existing data, AI does not generate new ideas. He noted that LLMs often make things up because it makes things plausible. For a mathematician, plausible is not enough. A proof must be true. Harrer believes knowledge should be free. He frequently publishes his work on Archive, an open repository, ensuring that a student in a developing country has the same access to his proofs as a professor at Harvard. When asked for advice, Harrer avoids grand philosophy. "Follow your nose," he tells students. He encourages them to pursue what they find genuinely interesting rather than what is strategic. He never planned to win a Fields Medal. He just thought the noise problem was cool. He also emphasizes the joy of the click. He describes the best moment in math as the moment when it all starts to click together. It is that quiet thrill when the chaotic pieces of a puzzle suddenly snap into a clear, beautiful picture. Today, Sir Martin Harrer works at EPFL in Lausanne and Imperial College London. He has not slowed down. In 2025, he joined the Simons collaboration on probabilistic paths to quantum field theory. It is a massive international project. He is now trying to do for quantum field theory the basic physics of the universe, what he did for the teacup, place it on a solid mathematical foundation. He is still listening to the noise. He is still building the tools to understand it, and he is still proving that, with enough patience, even the most chaotic signals can be turned into a symphony.